Okay, so let's take a look at existence of equilibria to make sure that they are around when we want to analyze a game. So existence is a very important property. Why is it an important property? Because if we don't have any equilibrium, then it's very difficult to make predictions about what's going to happen in a game. Whereas if we do have equilibria, then at least we can make some predictions about what might happen in a game. So the existence of equilibrium is an important question. And so one note is that every game we've really looked at so far in the course has had an equilibrium. And we might ask, is this a general property? Is this something that's true in a lot of cases or in cases of interest? And one of the most important theorems on this is a theorem by John Nash in 1950. And what he proved was that in every game where each player has a finite number of pure actions or pure strategies, so similar to many of the examples we've considered so far, there exists at least one equilibrium. And possibly it might involve mixed strategies, so it might be that the only equilibria are in mixed strategies, but every game that has a finite number of pure strategies has at least one equilibrium, one Nash equilibrium, possibly in mixed strategies. So this is the theorem that gave the name Nash equilibrium, the existence here. And in order to get a feeling for how this works, so we're not going to go through a formal proof of this. The proof of this theorem involves using fixed point theorems, which we're not necessarily going to assume that you know, but we can give you an idea of why this holds and what the sort of logic behind the proof is. And then you can look at some of the references in the syllabus for background and in particular for people who are interested in knowing a little more about existence. So why might this be true? So let's have a look, start by 2x2 games and understanding what's happening in the 2x2 games, and then the principles behind this are a generalization, but the logic can be seen in this case. So let's imagine that we have a situation where we keep track of, say the row player has a choice between up and down, the column player has a choice between left and right. We keep track of, say, the row player's payoffs A, B, C, D for these various entries. The column player has corresponding payoffs. So if we're keeping track of the probability that the column player plays right, for instance, so let's say the probability that the column player plays right, we keep track of that. Then we can keep track of what the payoff to up is. It's going to be 1 minus P times A plus P times B. That's the payoff to playing up. And the payoff to playing down, correspondingly, if we look back here, C if they're playing left, D if they're playing right, we're keeping track of that probability. Then we end up with 1 minus P. P is this probability of playing right by the column player on C plus P on D. So we get two curves again, just like we had before. And again, in this case, we get a situation where up is better, a situation where down is better, an intersection. Now it could be that in this game, so in this game we end up with these three situations. It could be that one of these curves is above the other one entirely, so you always want to play up or you always want to play down. But the important thing to note is that when we draw these out, we get a nice connected best response correspondence. So for each probability that we list for what the column player is doing, we have a choice of either up is better or down is better, or you're completely indifferent. And what that means is as we trace out what's going to happen, we're going to end up with a nice graph where as we march from the left to the right, I can draw this in a way where my pen does not leave the paper. So I move along, maybe I'm indifferent for a while, so any points where I'm going to switch between up and down, I'm going to be indifferent at exactly those points, and then I go in one direction or another. So when we look at mapping out these correspondences, we end up with a nice connected graph in terms of the best response correspondence of the row player, We do a similar analysis for the column player. And the idea here is that these curves, if I'm going to try and draw these, they must cross somewhere. So in terms of the row player, I'm marching along. If I'm moving from left to right, my pen doesn't leave the paper. I'm going from the left-hand side to the right-hand side. For the column player, I'm going from the bottom here up to the top, and my pen doesn't leave the paper again. If my pen doesn't leave the paper, and I'm going, one curve is going from the bottom of this graph to the top from this picture, right? So I start with 0 on this axis and move upwards. The other curve goes from left to right, and it doesn't leave the paper. Connected continuous curves have to cross somewhere. So generally, what we need is just a point where both are on their best response correspondences. Generally, there's a theorem that would tell us that as long as these curves are connected, we're going to have an intersection. The general version of that theorem says that if the best response correspondences are nicely behaved in terms of having this connected structure, and we're working in a nice space, then there's going to be a point where we're on everybody's best response correspondence at the same time. So we end up with a nice conclusion that there always exists at least one equilibrium. It might be mixed, it might be pure, but there's always at least one. There could be more, but there's always at least one. Okay, so we have a nice existence result. Nash equilibria always exist when we have a finite set of pure strategies. Do they always exist more generally? So sometimes, as we saw before in the course, it's nice to look at games where players might have an infinite number of strategies, not just a finite set. And unfortunately, equilibria don't always exist without some additional assumptions. So just to give one feeling for that, let's look at a very simple game that doesn't have a Nash equilibrium. Let's think of a set of players, and each player gets to name an integer. Okay? So each player yells out an integer, and whoever yells out the highest integer wins a prize. So you get a payoff of 1, say, if you are the person announcing the highest integer, payoff of 0 if somebody else announces the highest integer. Let's flip a coin in the case where there's a tie. So if there's, say, 2 players that tie, we'll flip a coin to decide who wins. So in that situation, well, you'd always like to be naming a number that's higher than anybody else's number. So whatever number one player announces, somebody else would like to announce a higher number. It's pretty easy to see that there's no equilibrium point. Whatever number, whoever's winning, the other player should change the strategy that they're announcing. So if one player announces 100 and the other announces 50, then the player who announced 50 should announce something bigger than 100. But if they announce something bigger than 100, then the other player should announce something even bigger. So we end up with no equilibrium in this game. So the question of existence of equilibria and Nash, existence of Nash equilibria is an active area of research. There are many different theorems for games with infinite strategy spaces, and depending on the structure, you need to put more structure on the game in order to say whether there does or does not exist equilibria. But there's quite a bit of research that's been done on that, and nicely behaved games tend to have equilibria. But what nicely behaved is a question for beyond our investigations here. Okay, so what we've done in terms of looking at Nash equilibria, we've gone through pure strategy Nash equilibria, understanding what they look like. We've talked a little bit about mixed strategy Nash equilibria. Generally, in games, there can exist multiple equilibria. In games with finite strategy spaces, there always exists at least one. So we have some predictions of stable points. And the nice part about Nash equilibria is if you're there, if we all anticipate that those are the strategies that are going to be played, then nobody has a reason to move away from that. So these are stable points. They're the points where we can make predictions that are going to be self-fulfilling. So they have very nice properties in terms of making predictions about outcomes of games.